My name is Stephen Donnelly. I'm from Indase. We're a proud sponsor of SharkFest. We have been for several years. We have a vendor table in the vendor area there during the dinners, so if you want to find out what we do, you can talk to us there. What I'm going to talk about today is packet capture metadata, which might seem kind of mundane, but hopefully by the end of the talk you'll understand why I think it's quite important, and you'll understand how you can use it in Wireshark and leverage it for your benefit. Okay, so why is packet capture important? If you're here, you probably are already doing it, so you already understand that. There's this great t-shirt from Net Reset guys. PCAP or it didn't happen. In fact, I think Jasper in the previous session was actually wearing that shirt. You can buy it on their website. But the point is that we treat packet captures as ground truth, right? It's evidential. If you're trying to prove to someone that there is a problem and explain whether it's a network problem or it's an application problem, having a packet trace is a great way of being able to demonstrate in a very clear way exactly what's happened. And so PCAP or it didn't happen is a great catchphrase. There's another saying which we've heard today already, which is packets don't lie. And I think you can get that on the shirt as well. And that's also a great saying. And I was talking to one of our customers once, and they had a bit of a twist on that. And what they said was, packets don't lie unless you don't know where they came from. And I sort of thought about that for a minute and went, yeah, he's got a point. And sort of tried to think about, are there cases where packet traces can be either lie, so they're deliberately misleading, or simply misinterpreted. So there's something about that packet trace where when you look at it, you jump to the wrong conclusion because you don't know all of the context around how it's captured. So some examples, packets don't lie unless you don't know where they came from, right? So if you didn't record that packet trace, somebody else gave it to you, do you trust them? Do you know where they actually did that capture within the network? Does it make a difference whether a trace is recorded near a client or near a server? Yeah, it does. It depends where you are in that network diagram. Packet traces can also be misleading if you don't know if there's packet loss. Okay? Because if there is packet loss during the capture process, then there's information you don't have. Sometimes you can infer that by looking at the packet trace, and some of the talks do cover that, but you can't always tell. There's also another case where you might have an hour-long trace file, and it says there were 10 packets dropped. Okay, well, where were they? Were they at the beginning, where maybe you don't care? Or were they scattered through the file? You can't actually tell from a single counter where was the packet loss. Is it going to affect what I'm trying to understand from this network trace? Packet traces can also be filtered. So I'm looking at a packet trace, there's no DNS traffic in the trace. Is that because there wasn't any on the link, or is it because it was filtered out? Either at capture time or post-capture by someone who's been looking at this trace file doing something to it. So if you're not recording that information about how the file has been processed, you're missing some of the context. But at least you can trust the timestamps, right? Well, maybe. Do we know if they're hardware timestamps or software timestamps? Do we know if they were generated from some upstream device? Do we know if there was a span in between? Do we know if the clock that was used to generate the timestamps was actually synchronized to anything? Was NTP running, or was it PTP, or what? So when you think about a packet trace, there's actually a lot of background that you need to understand in order to be able to interpret it accurately. And if you're just looking at a raw PCAP file, it doesn't have that context. So you need to write something down in a journal, and then if you give that file to someone else, they don't have that. So the answer to this is metadata, right? So we need some way of recording all that context in the trace file. So that's what I'm going to talk about today. Why do we need metadata? What's it for? What types of metadata are there anyway? Is it as simple as it sounds? And then how can we actually use Wireshark today to capture the metadata, to examine it and use that, leverage it to improve our understanding of the traces. We'll look at a couple of different formats. There's PCAP-NG, and compare that to regular PCAP, the original, and the ERF format, which is from Indase. Okay, so data needs context. There's a whole lot of different reasons why contextual metadata is quite an important thing. One of them is, in the old days, if you're just looking at an issue with your laptop, going into a data center, plugging in your laptop, running a capture file on one interface, that's fine. But today, we often have, we've got cloud, we've got lots of agents installed, we've got large data centers. A single packet trace may actually cover multiple points within a network, and you need to be able to distinguish those. Data mining, so anything where you're capturing a lot of data and then trying to analyze it after the fact, you need to record the context or else you can't understand what it is you're looking at. And talking about that sort of evidential quality of the packet trace, you need to understand what the quality of it was. Were the timestamps accurate? Was there packet loss? And so on. Timing accuracy is becoming more important, so particularly in the financial space. European Union has the MiFID II regulations that came in fairly recently that say that you have to be within a certain accuracy, so your timestamps have to be within, I think it's a microsecond of UTC, and you have to be able to prove it. So when you think about your typical PCAP file you've captured on a laptop, can you prove that you're within a microsecond of UTC? You probably can't. Big data, so more and more what people are doing is not just capturing a short trace file and looking at it on their laptop, they set up a big data warehouse, they set up a data lake, they capture all this stuff and pile it all in. Again, if you're not keeping very careful track of where all the data is coming from, then it's just a swamp, right? It's not actually very useful at all. And finally, event annotation as well. So there's metadata that we capture at capture time, but there's also integrating, correlating different sources of information. So if we've got an IDS system generating alerts, those kind of things, we want to be able to mesh those together with the packet data in order to be able to understand what's happening. Okay, so that's kind of some of the motivation. Why is metadata useful? And next we'll have a look at what we actually mean by it. So I think intuitively you kind of all understand what we mean by metadata. A good example is images. So they have tags, like key values stored inside the file. This is an example of a picture from SharkFest in Europe last year, which was in the Netherlands. And you can see on the right-hand side, perhaps not very clearly, there's some metadata there which Google is pulling out from the image file. And the kind of things that it has in it is the time that the photograph was taken, not just the file timestamp, but embedded in the picture when it was recorded. What type of device took the photo, so it's an iPhone in this case. Some of the technical details, what was the shutter speed and the aperture and the sensitivity and all that sort of stuff. And perhaps most importantly, a location. So it doesn't store the map in there, but it stores a latitude and longitude. And that's enough for Google to give us a place name and be able to draw the nice map. So based on the timestamp and the location, I can guess this was at SharkFest last year, even if I haven't recorded any specific annotations. Okay, so what sorts of metadata are there? I think when you think about this, you usually think about static metadata. So this is a snapshot in time. It's a piece of information which doesn't change during the time that the capture is occurring. So that's the kind of things like information about the system that's performing the capture, so the host system details, what the set of capture interfaces was, and the software versions. Those are not usually going to change while you're in the process of doing the capture. But something we sometimes overlook is dynamic state in the network. Examples of that, timing and clock synchronization is one of the main ones. So when I start capturing, the clock might be synchronized to some FTP server. But if I'm capturing for a reasonable period of time, there's a good chance that the state will change. So if we're not recording that periodically, or we're not recording the changes in the state, then that static metadata from the beginning of the capture is no longer accurate by the time we get to the end. Also, particularly for rolling captures, links come up and down. Interfaces might get added or removed from the capture. Optical power levels can change. Somebody unplugs a fiber somewhere, or there's a fiber cut. Digger goes through buried cable. And then the third sort of category of metadata, I would say, is post-capture. So those first two things are things that you might capture, record when you start doing the packet capture. But there's also things that happen afterwards. So the common case in Wireshark is somebody wants to add a packet comment, or trace file comment. and that's done after the fact. But you can also automate it, so you can have things like things like IDS alerts, for example, which might relate to specific packets. That information can be annotated back into the trace file after the capture is actually finished. And if you're doing some sort of data mining, some AI learning, you might be trolling through these files and inferring information about the trace and then recording that back into it afterwards. Understanding the kind of the history, the audit trail of what's happened to that file over time is quite useful. So, what are some specific examples on the kinds of metadata we might want to look at? This is not exhaustive, but it's a collection of some of the kinds of things we might be interested in. Obviously, we want to see the contents of the packets, but beyond that, there may be things like what was the filter that was applied at capture time. When was the packet recorded? Sure, what was the timestamp, but also what was the clock source? Was the clock synchronized to anything? What was the clock quality? Where was it recorded? So what was the host system that actually did the packet capture? Where was it in the network that we were looking at? What was the name of the link? If we were using a packet broker on that port or a span port, what was the configuration of that? Where's the location of the machine? If you're a large organization, you may have data centers all over the world. Understanding exactly where things are does make a difference. Possibly why? Why did we actually do this capture in the first place? Is it related to a particular ticket number, customer support request or something like that? It could have been a triggered capture generated based on an IDS alert or something like that. Also, again, in larger organizations you may have permissions around packet capture, so who actually requested the capture and who performed it, as well as the how. So that's kind of the easy stuff. That's what was the actual capture hardware, how was it configured, what version was it running, and what was happening on the network at the time. So what are the link states, optical power, things like that. So if that's the kind of thing we want to capture, how are we going to record that information and how are we going to store it so we can look at it later in Wireshark? So, first question for the audience, who's still doing packet captures in PCAP format? Anybody? A few people? Okay. And who's using PCAP-NG? Some of the same people, but also some other people. It's interesting. I think PCAP is still very common. It's been around for a long time. It's a lingua franca. It's an interchange format. A lot of tools still only support it. When we think about what's actually in it, it's very thin. So it's very easy for people to implement some tools, but it doesn't give us a lot of context. When you look at it, there's basically just two things. There's a file header, and then there are packet records. The file header's got a few things in it. It does tell you what the endianness is and what the timestamp resolution is. There's a time zone information, which may or may not be filled in. There's a timestamp accuracy field, which as far as I can tell, the PCAP never actually fills in at all. It feels unused. There's a capture length and a link time, and that's about it. That's all the information you get. There's nothing in there about what the host was, where it was captured, what was happening at all. And then on a per packet basis, you get the packet contents, the timestamp, the length of the packet, and again, that's about it. So let's see if we can do a quick demo. Now, we've all seen PCAP files before, but this is kind of a good benchmark because we are all familiar with it. Is that visible? No? Okay. Alright. So when we have a look at a packet in Wireshark, this is just a random capture file, it's nothing particularly interesting. If we open the frame dissector, this is all the information that Wireshark knows about the frame. Again, anything in square brackets is something which Wireshark has calculated itself. Anything that's not in square brackets is read out of the file. So you can see a lot of the things that are in here are things that were calculated by Wireshark. One thing that you notice, having a look at it, you can see the timestamp there, which is great. There's no interface ID. Right? So it doesn't tell us what interface we captured the packet on. PCAP can contain packets from more than one interface. But if it does, you can't tell, and you don't know which packet came from which interface. So if you're in Linux, for example, you capture from any device, that will capture packets from all of the interfaces at once. And it won't tell you which packet came from which interface. It can be quite confusing. So this is one of the reasons why PCAP is not a good idea for capturing multiple interfaces. Obviously, you try and stick to one if you can. The other place that we can get information about the trace file is in the Analyze menu. Statistics and capture file properties. I'm sure you can see that very well. This screen obviously doesn't scale very well. This dialog is Gerald talking about high DPI resolution support and all that kind of stuff. That's down to the windowing toolkit. But what it's basically saying is this is all information that Wireshark knows about the entire trace file. And there's a number of fields in here. A lot of them are marked as unknown, so I don't know if you can see that. These fields, it says capture, hardware, operating system, application, all unknown. The capture interface is unknown. The number of drop packets is unknown. The capture filter is unknown. It does know that the link time is Ethernet, which is useful. It knows the packet size limit, so the capture size that was done at the time. And then there's some statistics here, which are counters. And those are things, again, which Wireshark has calculated itself. So they're not stored in the file, it's simply read the file and it's counted up the number of packets. So not very much to go on in this case. Okay, so what does PCAP actually capture? Well, it gives us the packet contents and a timestamp, and it does tell us about the timestamp resolution for the file, so whether it's a microsecond or an nanosecond resolution PCAP file, and that's about it. So when you look at our kind of matrix of interesting stuff, it's not covering very much. So some smart people quite a long time ago had a look at this and said, this is not good enough, we need to do better, and they came up with PCAP-NG. So this is not a new thing, it's been around for quite a long time. It's a much more advanced file format, it's more complicated. It uses a tag links value scheme for encoding lots of different metadata fields and different types of blocks. So there's over 30 different types of tags which can be defined. The file format supports multiple interfaces natively and distinguishes between them, and it's an extendable format. So although there's around about 30 tags defined today, vendors can define their own tags, and the PCAP sort of industry group, if you like, can add more tags to the definition. So it's quite scalable in the future. There were a couple of IETF drafts, 2004 and 2014. So it does go back, over 10 years. Neither of them were accepted as RFCs, as far as I know. And PCAP-NG has been supported for reading. It's supported in Wireshark since 1.2 in 2009. It's also readable directly by libpcap since 1.1, and it's the default output format in Wireshark since 1.8, which is back in 2012. So if you're using Wireshark or DumpCap to capture packets, by default it's going to put them in PCAP-NG format, and you're going to get quite a bit of metadata by default. The standard for PCAP-NG is on GitHub, so you can go to the GitHub link there and actually get a copy of the current format definition. So how does PCAP-NG work? PCAP-NG defines a number of different blocks, section blocks. So there's a section header, which is kind of like a file header. The things which are in bold there are required, and the things that are in italics are optional within a block. So a file has to have a section header block, and it has to have a version in it. Optionally, it can contain the hardware, the OS, and the application. Those are the fields that we saw in Wireshark before that were marked as unknown. So that's where that information gets stored in PCAP-NG. For each interface that exists in the capture file, there's an interface description block that tells you some information about it. Again, there's only a few things that are mandatory, but there's quite a few optional fields. So you can name the interfaces. So that's immediately very useful. It can also give you the address of the interface, if it has addresses, what the speed of the interface was, timestamp resolution, any filters that were applied on that interface on a per interface basis, and so on. Then the packets themselves are stored in what's called an enhanced packet block. There used to be a simple packet block, they got rid of it because it wasn't very useful. The enhanced packet block for every packet has the contents of the packet, a timestamp, and interface ID. And there's a few optional fields like packet drops and flags and errors and things like that. And there's a name resolution block. So the name resolution block is a way of storing within a trace file what an IP address, for example, will resolve to, so what the name is associated with that. There's also an interface statistics block, which can be used, which is on a per interface basis. So if I have a PCAP-NG trace file with 2 interfaces in it, there'll be 2 statistics blocks, one for each interface, and it will count, typically it has the start and end time for the period covered, and then a number of counters. There's also a whole bunch of experimental blocks, which were proposed in the original definition back in 2004, but have not been implemented by anyone. So they're kind of open for discussion, I guess. Things like compression, encryption, indexing, statistics, so extending the interface statistics block, events, and vendor extensions and things. So there's plenty of room for extension there. What does it look like? So the way Wireshark in a sense only implements a subset of the standard, but it's the most widely used implementation of the standard. This is roughly what it looks like. So when you look at a file in PCAP-NG format, you start off with a section header block. Wireshark, I believe, currently only supports one section. So the standard allows you to have multiple sections, one after the other, but Wireshark just has one for the entire file. Then there's a number of interface description blocks, one for each interface that's used in the capture file. Technically, they just have to occur before a packet from that interface occurs, but Wireshark always puts them at the start, so that's nice and simple. And you have a number of packets, each packet its own block, and then at the end of it you can have name resolution blocks which map network names to addresses. They can be up to 1 megabyte in size each, and if there's more than 1 megabyte of name resolution, then it'll simply create more. And then finally, for each interface in the capture file, there's one interface statistics block that gets added at the end. And that's basically equivalent to those counters that we saw in Wireshark before. Okay, so let's have a quick look at the PCAP-NG file. Okay, so here's a PCAP-NG file. And again, we look in the same places. So one of the things we see, one of the things we can see here is there's interface ID. So every packet in the trace file, there's a couple of different interfaces used in this trace file, has a name. Now this particular file was captured in Windows, so the name of the interface by default is device NPF and then some GUID. Now the thing about GUIDs is they're not very meaningful to people, but at least they're unique. If you do a PCAP-NG capture file in Linux, then what you get is the local name of the interface. So you get ETH0 or ETH1 or something like that. So it's more understandable to humans, but it's actually not globally unique. So it's a bit of a trade-off there. You kind of get one behavior in Windows, different behavior in Linux. Perhaps there's a feature request for core developers in there somewhere. Okay, the rest of the per packet information is pretty similar. There's nothing particularly special in here. And if we go back to the statistics menu, capture file properties, again, I appreciate it's a little bit hard to see. The slides that are available later will have screenshots in it, so you can look at those. But what we see here is some more of these fields are now filled in. So under capture hardware, it still says unknown, which is a bit of a surprise. In Windows, Wireshark doesn't record anything in the capture hardware field. If you're in Linux, what it does is it puts the CPU type in there. So it'll say something like, genuine Intel i7-4700U at 2 gigahertz, which may or may not be useful to you. That's what Wireshark will currently put in there. So again, a bit of behavior difference between Linux implementation and Windows. Macintosh I couldn't tell you, unfortunately, somebody would have to try. The OS, so 64-bit Windows build, the application is listed as dumpcap. So when you're capturing Wireshark, the application that's actually capturing the packets is dumpcap. which is formed by Wireshark to do the capture at a lower privilege level, and gives you the version. So it's dump cap, which is part of Wireshark 2.2.7 in this case. And then it lists the interfaces, and again, these are these horrible Windows GUID interface names, but at least we can tell that there are two different interfaces in here. It lists the number of packets that were dropped on a per interface basis. So here it's saying it was one packet dropped on one of these two interfaces. You also can record EPF capture filter on a per interface basis. So when you start a capture in Wireshark, you get the option to set a capture filter on each interface, as well as the link type and the packet list, the packet size now. And again, the counters at the end. So these counters are not on a per interface basis. Those are global counters for the whole file, whereas the ones which are recorded in PCAP-NG are on a per interface basis, but those are not actually exposed anywhere. So one of the things a couple of other things. So there's a file comment here. So this is a comment which is stored in the section header block, which was add name resolution. So that's the comment that I put on there. So you can just type something in there and you can save the file. Next time you open it, that's still there. If you try and do that in PCAP, I think it lets you type a comment in there, but when you save the file, it's not saved. So if you reopen the file, it won't be there anymore. Okay, so now one thing you may notice looking at the packet list is where are all the blocks that I was talking about? So I said there's a section header block, and there's an interface description block, and all of these things. You can't see them. Wireshark is reading the file and interpreting all of that stuff, stripping out the interesting stuff in the background. But what if I want to see what's in there? It turns out you can. I only discovered that this week. So if in the view menu, there's an option down the bottom, reload as file format /capture. And when you open a PCAP-NG file, it opens it as a network capture, and the packet list shows you all the packets. But if you hit that toggle, what will happen is the packets will suddenly disappear, and we get a single entry in here which corresponds to the whole file. If we open that up, lo and behold, here are all of those blocks that I was talking about. So you can see the section header block, the interface description blocks, each of the packets. And you can open up each one of these, look at the block data, and it shows you all of the fields that are filled in. And each one of these, again, you probably can't see at the bottom left-hand side, these fields are all fully dissected. So regular PCAP dissector, you can use display filters, anything like that. So this particular one is pcap.options.option OS description. That field there. So all of the things which are visible in Wireshark are actually in there, including, if we scroll down to the end, you can see the name resolution block. So this particular file was recorded with name resolution turned on and then saved. So what Wireshark has done is recorded all of the resolved names. We can open this up, it's an extra 500 bytes. And it lists all the IP addresses that it was able to resolve. We open those up, we can see the names that it was resolving to. So you may notice that's a RFC 1918 address. So the resolution of that name is not public. So this is one of the reasons why saving name resolution is really useful. If I'm recording on a network that has a private address space, and I take that file away and try and resolve the names outside that network, I'm not going to get the names resolved. So if you do the name resolution on the network you're capturing on, and then save that, then you can refer to it later. We can switch back to the file format view. There is another way to see what's resolved. If you go to statistics, resolved addresses, there's a list in here of all of the host names that are resolved and what they're mapped to. The difference is this list here doesn't tell you whether the name was resolved locally by this running copy of Wireshark or whether it was read from the file. So if you want to know where did these names come from, were they resolved just now or were they resolved when the file was saved, you can switch to that file view and look at the name resolution block. So, what does PCAP-NG cover then? So it covers a lot more of the space that we're talking about, as well as just the packet contents. We get things like there's optional flags available per packet, whether there's an error in there or not. You can get a packet payload hash, that calls the packet filter for each interface. There is an interface ID, which tells you at least which interface within the host system it was capturing on. There's support for user comments, so you can add a comment to a particular frame. It gets added as a comment inside the packet block. And there's information about, depending on which platform you're capturing on, you get the hardware model, the OS, the application, and the link speed. Link speed is kind of important. I mean, if I see a spike up to 800 megabits, is that a problem or not? Well, it kind of depends. Was it a 1 gig interface or a 10 gig interface? Right, or a 100 gig interface? And without knowing what the link speed was, you don't know whether that link is actually saturating or not. So it can be quite useful. Okay, so that's PCAP-NG. Now, the interesting thing is that there are some things which are not covered here. So we don't know what was the clock source, what was the sync state, what was the system that we were capturing on, some of those things. Now, the good thing about PCAP-NG is it supports comments in any of the fields. So what you could do is you could write a capture comment, and you could note down some of those things when you do the recording PCAP-NG. So it's kind of a get out of jail free card. Problem with that is it's a manual process. You have to remember to do it. People are not very good at process and remembering, oh yes, when I capture this, I have to go and write this 3-page comment in the file talking about where I was and what I was doing when I had for breakfast and so on. Okay, so as far as I know, there's only one other capture format in Wireshark which supports comments and supports rich metadata, and that's the ERF format, which is Extensible Record Format or Index Record Format, and it's the format that we support in our products and appliances and so on. So I'm going to talk a little bit about that. One of the questions when I gave this presentation earlier was, well, why did you do some work in your own format rather than just extending PCAP-NG? And the answer to that, I think, is our format is, as I said, produced by our equipment. It actually predates PCAP-NG. It's actually even older than PCAP-NG is. And we control it ourselves, so it's much easier for us to try things out, experiment. And because we're kind of a vertical stack, we build our own hardware as well. So software, we have access to all of the metadata quite easily, so it's easy for us to add a whole lot of extra information. So how does it work? It's a stream of records. It's not a file format, so it's much more of a streaming format. It's been supported in Wireshark since it was called Ethereum, from 2003. There's full support for it in modern Wireshark, so 2.x. You can capture from a DAG card within Wireshark through the PCAP, and it's a fully dissected format. So all of the metadata that's available in the ERF format is dissected, and it's available for display filters and that sort of thing. Metadata support for ERF we've added relatively recently, so Wireshark 2.2 in Europe, 2016. And as of 2.4 we support file comments and packet comments and things as well. So what does it kind of look like? So we've added a new record type, which is called provenance record type. And we use it for both periodic metadata and event-based metadata. So periodic metadata is useful for recording dynamic information. So links are going up and down over time. Then you can record that, say, every second within the packet trace file. We support different types. So there's per interface information. There's you can have flow-related information. You have packet-related information. It has a kind of a hierarchical addressing scheme. So rather than just talking about what interface we capture on, we talk about what was the host that was captured on, which capture card within the system are we talking about, and which interface within that card are we talking about. We record the time that the metadata was generated because it might be post-event. It might be post-capture metadata. So if you come back and you annotate commented afterwards, you want to know when was that comment added. It's basically a TLV format similar to PCAP-NG. It's encoded slightly more compactly, but it's otherwise very similar. We have a number of different sections, which are similar to blocks in a way, with information relating to the specific capture, the host, and module, and so on. It's a TLV format. There's over 160 tags defined. We basically just sat down one day and thought of every piece of information we could think of that might be useful to record. I think it's grown a little bit since then. We're probably up around 180. There's up to 64K per record. And the idea is that if you need to modify a piece of information, you leave the existing information there and just append a new record with the updated information. So we're going to maintain an audit trail of changes to things over time. So what does that look like in a trace file? Here's an example. So you've got some devices producing the stream of records. So there's no file header, but what we're doing is periodically inserting metadata records. An example would be one specific. So we start off the capture, put a metadata record in that describes the whole system in the current state, all those dynamic things, and then capture some packets, and then periodically reinsert that data with updates for any dynamic changes that have occurred. Some of the examples of the things that are in there, so capture section, the name of the capture, description, the application version type, which is similar to the section header block in PCAP-NG. The host, so record a lot more information about the host system. What was the name of the machine, what was the model, the serial number, what was the organization, so within a single company you can kind of configure your systems to record that information. And location as well. The module or capture device, so within a particular capture device, what was the model, what was the firmware that was running on that device, how was it configured, if it has clock synchronization in the hardware, how was that configured, who's it talking to, what's the error estimates, and then the per interface section. So on a per interface basis, record information about pluggable transceiver models, vendor, serial numbers, receive optical power, addresses assigned to the interface, all that kind of thing. And then on a capture stream or a capture queue basis, what's the buffering size that's been allocated, have there been any packet drops, all that kind of thing. Okay, so what does that look like? Find the ERF file. Okay, so first of all, we can pick a packet at random, and we can see there's an interface ID, highlight it there. It looks a bit different, so you've still got the interface ID number, which is 0, that's assigned by Wireshark, and then you've got a name string, which includes this hierarchical address. So you've got the friendly name of the interface, which was just called port A in this example, which is a default. Then we've got the host ID, which is a 48-bit globally unique number. The source ID, which is referring to which capture card or capture device within the system that we're talking about. And then an interface ID, which is which interface on that capture module we're talking about. So this was a system which had 2 4-port cards within it. So it's talking about the second card, interface A. And every packet has got that information recorded on it. Also, if we go to our statistics, capture file properties, we can see that information has been read out by Wireshark the same way that it has in PCAP-NG. So for the hardware line, which in Windows is normally blank, it has the name of the machine in the description, so systems test 8000-2, and then it has the CPU information and tells you on blah blah blah, which is similar to what Wireshark will record in Unix, in Linux. Uses the same information. Then the OS version, so this was captured in CentOS 7, and the application that generated the metadata was called DAG-Meta in the 5.5.1 release. The information on a per interface basis is the same, so we see the interface name, drop packets, capture filter, the link type is just listed as ERF, packet size, and characters. You can also put capture files comments in. And what it will do is it will record that inside the capture section of the provenance records. So if you type something in there and save the file, it'll actually update all of the provenance records in the file. Why would that be useful? What's the point of having that information redundant, repeated through it? Well, if I've got a trace file that's a couple of hours long, and I just want to generate a clip out of the middle of it, I can just clip out those packets, and as long as it goes over a second boundary, I've got a copy of the metadata immediately. I don't have to go and find it from somewhere else. And it's the metadata that's up to date with that time period that I'm looking at. So another thing that we see looking through the packet list is periodically we're seeing these ERF metadata record entries. So unlike PCAP-NG, where the blocks are hidden, in the ERF, the metadata records are actually dissected as if they were packets, so they show up in the packet list. Squash the time field, but if you look at the timestamp on that metadata record, it's at 4845.0000. And if you look at the next one, it's at 46.0000. So it's putting one of these records in exactly on every second boundary, as close as we can. So if you opened up, have a look at what's in there, you can see a number of things. There is the timestamp that the metadata was generated on. So this metadata was from a year ago, so October 2016. We can see the capture section, which tells us about the whole packet capture in total. We've got a name, so it's example capture, description, the user who was actually doing the capture, so the admin user, the name of the application that generated metadata, the time zone offset, so this was recorded in New Zealand, so NZGT, daylight time, and the number of seconds offset from UTC, what that is. So the timestamps in the file are in UTC, but if I wanted to display them in the time zone of where the file was recorded, you can use that information to set the time zone in Wireshark, for example. Information about capture host, so we've got the host name of the machine, description field, the organization with index and location, the model of the machine, the amount of RAM that's installed, 127 gigabytes, types of CPUs, number of cores, operating system, and the DAG software version, which is the index software version. The capture module has information about the capture hardware that was used, so the model of the device that was used, what firmware was it running, what was the build time for that, serial number of the device, what was the flow hashing mode that was enabled, so how was the card actually configured. And also, interestingly, it has information about clock synchronization. So it's telling us here that at this particular time in the trace file, the clock's not synchronized. Okay, so at that particular time, the timestamping clock we're using for recording packet timestamps is not synchronized. And because of that, the clock errors are zero. And the clock source that's configured is a PTP source. And then we can look at the interface sections. It tells us about each capture interface. So the capture interface called port A, in this case, is actually a 40 gigabit Ethernet interface. So it's actually consisting of 4 10 gigabit SFPs getting together to form one 40 gigabit interface. So it's telling us the make and model of each of those 4 modules, as well as receive and transmit optical power levels and so on. Second interface on that card is a PTP timing port. So it's a 1 gigabit interface, there's a copper transceiver in it, and it has an IP address assigned, which you can see there, and you can see whether the link is up or not, so the link is up here. And then finally the stream sections, so these are the capture queues, if you like, so where the packets go when they're being captured. You can see that it has a 64 megabyte buffer assigned, and that there's 0 packet drop on that stream at that time, so that's being updated each second. If we zoom through the file a little bit, pick up a metadata record near the end, if we have a look at the capture section, we can see that while that capture was running, the clock synchronized. And we can actually track the performance of that, or the progress of that synchronization through the periodic metadata records. So by the time we get to the end of the file, the clock is synchronized, and we scroll down a little bit, we can see that it's using PTP, it's PTB is estimating 18 nanosecond offset from UTC, from its Grandmaster. We get the ID of the Grandmaster, which is a Symmetricon GPS receiver. It tells us that it's GPS specifically. It tells us the PDP is the slave mode with end-to-end timing, and what the clock accuracy class is. So the PDP Grandmaster is saying this Grandmaster is advertising accuracy to within 100 nanoseconds of UTC. And that's all recorded on a periodic basis. Okay, so if we go back to our coverage, we're covering more of the fields, I think, probably not quite everything. I've drawn a distinction here between the capture filter and the display filter. So with PCAP-NG, we're recording what the PCAP filter is on a per interface basis. And you do the same thing here with ERF. What we're not recording is a display filter. So what I mean by that is, if you load up a PCAP-NG file, and it had a filter applied when it was captured, that's recorded in the file. If I do a display filter and then export the packets under a display filter, that's not recorded. That's not covered by the fields that are in PCAP-NG today. So again, possibly an enhancement request if there's any core developers looking for something to do. I think that would be a useful addition. Similarly, packet broker. I think it would be really interesting to be able to get some of the information from packet brokers and actually embed that in the trace file as well, so we know that when a packet came from an upstream port on the packet broker, or the link speed of that, whether any drops at the packet broker, for example, that kind of thing. Okay. So both of them support comments. PCAP-NG has a string comment which can be applied to any block type. Wireshark implements comments in the section header as a trace file comment, and it supports packet comments. You can support comments in any of the field types, but Wireshark doesn't display them internally anywhere. You have to go into that file view and actually dig down to try and find them. And it doesn't have an interface for setting them either, for that matter. ERF, with provenance records, any type of tag can exist within any section. There's not a fixed mapping, unlike PCAP-NG. You can put, so you can put a comment string anywhere you want, and because it's dissected, you can find it, it's just visible on the packet list. And the way that we deal with Wireshark integration is, as I said, if you record a capture file comment, it just gets put into the capture section of all of the provenance records. If you want to add a comment to a particular packet, what we do is we generate a new provenance record just before that packet, and put the comment into the provenance record and then attach it to that packet. So there's a little anchor that links the two of them together. And as well as the comment that you're adding, we also record some metadata. So we record the time at which you added the comment, and we record the user ID of the person who's logged into Wireshark at the time who recorded the comment, and we also can record a host ID for the system that was used to add the comment. So if you're sharing files between a number of colleagues in a larger environment, it's really useful to know who added what comment at what time. Okay, so a little bit of comparison between the two. Please don't take this as a beat up on PCAP-NG. These formats are both very good. They're both supported today in Wireshark, and they're both extendable. So there's nothing stopping somebody defining a similar set of tags in PCAP-NG, so they can be equivalent. I think the difficulty that you would find with PCAP-NG is PCAP-NG has to, and Wireshark in particular, works on a number of different platforms. So it works on Linux, Windows, Macintosh, and it has to work on all kinds of different packet capture hardware. So finding common APIs or portable APIs for collecting all of that metadata information will be harder in PCAP-NG. But if somebody's interested in it, I think it can be extended. PCAP-NG then, I would say, is well suited for kind of ad hoc capture. It's a file format, it's intended for a limited period of time. It works very well when short capture, where the dynamic information is not changing very much over the period of the capture. It's pretty lightweight, which is good. It does support multiple interfaces that the PCAP doesn't. ERF, on the other hand, is more of a streaming format, so it's good for continuous packet capture. So rather than doing just plugging your laptop in and doing a short capture, you just have a rolling capture that's running all the time. The fact that the metadata is updated periodically makes it very easy to extract particular time periods within a trace file. It's fairly lightweight. It's one extra record per second per capture device, which is relatively low overhead usually. Supports multiple hosts, so if we've got customers with hundreds to thousands of capture probes within a fabric, and at that point, one capture file may contain packets from a number of different sources. So you really do need to track where all the packets come from. So it's much better for a dynamic kind of environment where links are going up and down, people are changing configuration in the file. So conclusions, packet metadata, trace metadata provides really important context. You can't interpret a trace file successfully unless you know where it came from, how it was captured, what the quality of the trace file is. There's different types of metadata. Automatic metadata is better than manual metadata. So yes, in PCAP-NG you can get around a lot of things by just adding comments, but unless you remember to do it, then it's not there, you can come back to look for it later. So the more that can be automated, the better. And both of these things are supported in Wireshark today. So PCAP-NG has been the default save format in Wireshark since 2012. A lot of that stuff is already there. You could leverage file comments by manually putting things in. So I really encourage people to capture in PCAP-NG if you possibly can, rather than PCAP. And if you're sharing files with colleagues, try and use a format with metadata support, like PCAP-NG, rather than just PCAP. Okay, remember to you at lunch. There's a couple of minutes for questions, I think. Also, I'm around for the conference and I'll be at the stand later on, so you can drop by and say, ask any questions you want. So, any questions on that? Good. One, yeah.
Two questions. First is what brains do you support for NPD?
What brains?
Yes.
Is that?
Do you support like PCAP-NG or for the specific?
Good question. So we're agnostic. We're a capture device. A network packet broker can come from any vendor, and then they send records to us.
No, I mean the specific header or threader they put inside the packets, and this is specific for brain. So every vendor is putting something differently.
Right. Okay. So the question there was different packet brokers typically add information to packets with a trailer or a header or a trailer, something like that. And what do we support for that? In terms of our hardware, our appliances, they capture the entire frame as they're received from the packet broker. So you will get the trailer from the packet broker, and it'll have the packet broker timestamp and the interface ID and so on in it. We're not doing any further interpretation with that. We just take it as it is and record it. So if your tool understands it, Wireshark has some dissectors for some of those trailers, and we'll pick that stuff out.
So you don't populate your metadata from this?
At the moment, no.
Okay.
I would like to do that. It's a good idea. Do you have a second question? Or?
What is the performance of the real performance of your card? Are you able to do a wire speed on 10 gigabits, 40 gigabits, 100 gigabits?
The question was, I think, what was the performance of the packet capture device?
Of the card.
The card?
Yeah, the capture card.
Right, so they're designed to be line rate. Right, so they will capture all of the packets, minimum size, full line rate. You have to have something to do with them, right? So you can capture them into memory at 40 gigabits. Can you write them to disk, or can you analyze them in real time? That's a more difficult problem. But yes, you can definitely capture them. Anyone else? Otherwise, I think we'll break there and we'll go to lunch. Cool. All right, thank you for coming.
you.